Today we're going over the summary and review of Unit 2. If you find value in this video, please like it and let people know about the channel because it really does help spread the knowledge. In Unit 2.1, we introduce the concept of atomic matter. The word atom or atomic was derived approximately 2,500 years ago by Greek philosophers. They thought that matter in our world was composed of tiny atomos, which translated means indivisible particles. This theory was replaced by Plato's and Aristotle's theories that there were no indivisible particles and that all matter could be divided into smaller bits. There was soon to be a reemergence of this atomic theory in the 1600s when alchemists and chemists learned that they could measure amounts of specific elements by reacting them to form compounds. John Dalton was instrumental in this in the early 1800s and laid the groundwork for atomic theory. In it, he stated 4 rules. 1. Every element is composed of tiny subunits called atoms. 2. Every atom of a specific element is the same, but atoms of different elements are different. 3. You cannot change atoms of a specific element into atoms of a different element by chemical changes, and those atoms are not created or destroyed in chemical reactions as well. 4. Atoms can combine to form compounds, and these compounds have the same relative number of and types of atoms. This leads us into Unit 2.2, which goes over atomic structure. Although John Dalton and his 4 rules for atomic theory laid the groundwork for the theory, the rules were based on tests and observations he made in the laboratory, and he never published any proof that these atoms actually existed. As time went on, scientists got more advanced, and this atom started to become more visible, complex, and it became clear that there were subatomic particles. The first subatomic particle was the electron and was discovered in 1897 by J.J. Thomson. Electrons are negatively charged, are present in all elements, and play a crucial role in electricity. They are much smaller in mass compared to the other subatomic particles, being approximately 1/2000th of the mass. The proton, a positively charged subatomic particle, was discovered next in 1919 as the counterpart to the electron. It has a mass roughly times 2,000 times greater than the electron. Shortly after, in 1932, the neutron was discovered. It has a similar mass to that of the proton, but carries no charge. To aid in remembering their properties, one can associate the letter P with proton, indicating the positive charge, while the word neutron contains the letters NEU, indicating its neutral charge, and the electron is the only one left with a negative charge. These discoveries led to the development of the nuclear atom model. According to this model, atom consists of a central nucleus containing protons and neutrons, which accounts for almost all of the atom's mass. The electrons, on the other hand, are located outside the nucleus and occupy most of the atom's volume. As stated previously, protons and electrons have a charge to them, and you'll often see them with charges of +1 and -1 respectively. This is just for convenience sake, since they are equal in charge but opposite in sign. Another simplification in chemistry with subatomic particles deals with their masses. Because the masses are extremely small, we created atomic mass units, AMU, where 1 AMU equals 1.66054 times 10 to the negative 24th grams. Protons weigh 1.0073 AMUs, neutrons are 1.0087 AMUs, and electrons are 5.486 times 10 to the negative 4th AMUs. This leads us into what makes the atoms of one element different from those of another. Fundamentally, it's the number of protons in the nucleus of that atom. The number of protons is the element's atomic number. Since atoms don't have a net positive or negative charge, there is the same number of electrons as protons. However, the numbers of neutrons of an element can vary. For example, with carbon, there are 6 protons and in most cases 6 neutrons. Since the protons and neutrons weigh approximately the same, the relative mass can be stated as 12, 6 plus 6, which we call the mass number. Other atoms of carbon can have 7 neutrons or even 8, which give the mass numbers of 13 and 14 respectively. The atoms with differing numbers of neutrons are called isotopes of each other. This leads us into Unit 2.3, which goes over atomic weights. Atoms are technically small bits of matter, so therefore they have mass. However, atoms of different elements do not always weigh the same. For example, 10 grams of water with its chemical formula H2O has 1.1 grams of hydrogen and 8.9 grams of oxygen, even though there are twice as many hydrogen atoms, think H2, compared to oxygen atoms. Therefore, an atom of oxygen weighs approximately 16 times more than a hydrogen atom. Another way to calculate the atomic weight is through the use of atomic mass units. Let's run an example with the carbon-13 isotope. Remember from the previous unit that isotopes were atoms with the same number of protons, but a different number of neutrons. These isotopes vary in abundance, meaning that some isotopes are rarer than others. For example, with carbon, 98.93% has 6 neutrons, which we call carbon-12, and 1.07% has 7 neutrons, carbon-13. To determine carbon's atomic weight, we just multiply the masses by the percentages to get the average mass. This looks like 0.9893 times 12 AMU plus 0.0107 times 13.00335 AMU to equal 12.01 AMU. Note that carbon-13's mass equals carbon's 12 mass plus the mass of a neutron. This leads us into Unit 2.4, which gives a short introduction to the periodic table. As more and more elements were discovered by scientists in the 19th century, efforts were made to find patterns in order to classify the known elements in a systematic and predictable manner. These efforts resulted in the periodic table. The periodic table was developed by arranging all known elements in order of increasing atomic number. Remember from previous units, the atomic number is the number of protons in an atom's nucleus, and this is what determines an element's chemical property. The first version of the periodic table was proposed by Russian chemist Dmitry Mendeleev in 1869 and has since been revised and expanded as new elements have been discovered. The periodic table organizes elements into vertical columns called groups and horizontal rows called periods based on their electron configurations and chemical properties, allowing scientists to make predictions about the properties of elements that have not yet been discovered. The first period or row only contains 2 elements, hydrogen H and helium He. This first row only has 1 electron shell, which will go into more depth in future units. As you go down periods or rows to the second and third, an additional electron shell is added to the atom. The vertical columns, called groups, are labeled somewhat arbitrarily, but as you go from group to group, there is 1 additional proton and electron in the atom. This can get somewhat tricky to keep track of with the layout of the periodic table. For example, hydrogen has 1 proton and electron, while helium has 2 protons and electrons. Lithium has 3 protons and electrons. Beryllium has 4 protons and electrons. Then magnesium has 12 protons and electrons. The next unit, 2.5, introduces us to molecules. Technically, the atom is the smallest model of a single element, but in reality, only a few elements called noble gases are found naturally in this form. Most commonly, matter is in the form of molecules or ions. Molecules are formed when 2 or more atoms bond together chemically. This molecule can be made of the same element, such as oxygen or nitrogen, which we represent with their chemical formulas O2 and N2 respectively, and call diatomic molecules. They can also be a mixture of elements, which we call molecular compounds such as H2O, water, and methane, CH4. Molecules can also be pictured via their structural formula like this. In the case of water, the lines from the hydrogen H's to the oxygen's O's represent covalent bonds, electrons being shared, with each being 2 electrons, so 4 electrons in total, in those 2 bonds. The same goes for the bonds in methane. However, the 4 bonds represent 8 electrons, 2 each. We'll go over how to know the correct way to draw molecular formulas in the upcoming units. This brings us into the introduction of ions in Unit 2.6, which play a critical role in many chemical reactions and biological processes. Ions are atoms or molecules with an unequal number of protons and electrons, thereby creating an overall electrical charge that is either positive or negative. It is important to remember that chemical reactions generally do not change the nucleus of an atom where the protons and neutrons are. However, atoms can gain or lose electrons quite easily, forming these ions. Positively charged ions are called cations, while negatively charged ions are called anions. To see how cations, positively charged ions, form, we can look at the potassium K atom. Potassium has 19 protons and 19 electrons, and quite easily loses an electron, we'll go over why in the upcoming units, to have only 18 electrons. Since there is a net additional 1 proton, the ion has a +1 charge denoted in the superscript. The plus means +1 with each increasing net proton. The positive charge increases to 2+, 3+, and so on. The opposite is true in gaining of the electron, which we can see in bromine. Bromine has 35 protons and 35 electrons, and quite easily gains an electron, again we'll go over why in the upcoming units, to have 36 electrons. Since there is a net additional 1 electron, the ion has a -1 charge denoted in the superscript. The minus means -1, and with each increasing net electron, the negative charge increases to 2-, 3-, and so on. Ions can also form between multiple atoms, which we call polyatomic ions. Some examples of this are ammonium, NH4, with a +1 charge, made up of 1 nitrogen and 4 hydrogen atoms, and phosphate, PO4, with a 3- charge, made up of 1 phosphorus atom and 4 oxygen atoms. Fortunately for chemists, we can look to the periodic table to predict ionic charges of the many atoms. The elements of group 8A are called noble gases and are called this because they tend not to react with other elements due to their stability, which comes from the number of electrons they have in their outer shell. Elements close to this column will either gain or lose electrons proportionately to have the same amount as these noble gases. For example, the previous example of potassium and bromine in the periodic table, we can see that both are 1 electron away from the column. Potassium loses 1 electron to have the same number of electrons as argon, Ar, and bromine gains 1 electron to have the same number of electrons as krypton, Kr, which was exactly what we saw in our examples. Keep in mind, elements can gain or lose more than 1 electron to form ions. For example, magnesium, Mg, will lose 2 electrons to have the same number as neon, Ne, and oxygen will gain 2 electrons to have the same number of electrons as neon, Ne. This leads us into ionic compounds. As the name suggests, ionic compounds are chemical compounds composed of ions. One of the most common ionic compounds is the one that you ingest on a daily basis, sodium chloride. Sodium chloride, NaCl, more commonly referred to as salt, is composed of the Na+ ion and the Cl- ion. Due to the attraction between the equal but opposite sign of these ions, they form an extremely stable bond called the ionic bond with a net 0 charge. The stability is demonstrated in its melting point temperature, which is 801 degrees Celsius. Ionic compounds can also form between more than just 2 atoms, as long as the net charge equals 0. For example, magnesium Mg will lose 2 electrons having a 2+ charge, which can form ionic bonds with 2 chlorine ions, -1 each, to form MgCl2. Unit 2.7 gives an introduction to naming compounds. Chemists use chemical nomenclature, a classification system, to name chemicals and maintain organization. In the past, chemists relied on common names for substances such as water for H2O and ammonia for NH3. However, with the discovery of over 175 million unique chemical substances, it has become necessary to transition away from common names to a more systematic naming system. The chemical nomenclature system is divided into 2 main categories: organic and inorganic compounds. Organic compounds consist of carbon and hydrogen atoms, and their naming rules will be covered in the next unit. On the other hand, inorganic compounds encompass all other chemicals. Inorganic compounds are further classified into three categories: ionic or binary compounds, molecular compounds, sometimes referred to as ternary compounds, and acids. These classifications help in systematically naming and categorizing different types of chemicals. In the previous unit, we learned about ions, which are formed when one element loses electrons to become a cation, and the other element gains electrons to become an anion. Most cations are formed by metals, particularly those in the alkali metals and the alkali earth metals located in the first two columns of the periodic table. Cations formed from the metals typically have the same name as the metal itself, such as the lithium ion or the calcium ion. However, some metals can form multiple types of ions with different charges. In such cases, the metal name is retained, but Roman numerals are added to indicate the positive charge. For example, CO2+ is called the cobalt-2 ion, and CO3+ is called the cobalt-3 ion. In some instances, the Latin name of elements are modified with the suffixes OUS and IC. The OUS suffix denotes the lower of the two charges, while the IC suffix represents the higher charge. For instance, Fe2+ is referred to as the ferrous ion, and Fe3+ is called the ferric ion. Similarly, Cu+ is known as cuprous, and Cu2+ is called cupric. Cations derived from nonmetals are named using the suffix IUM. For example, H3O+ is called the hydronium ion, and NH4+ is referred to as the ammonium ion. When naming anions, there are a few different rules to follow. If the anion consists of a single element, the ending of the element's name is replaced with IDE. For example, H- is called hydride, O2- is called oxide, and N3- is called nitride. Naming polyatomic ions can be more complex, mainly because their naming system was established long ago. Polyatomic anions that contain oxygen have their name ending in ATE or ITE. The ATE ending is used for the most common oxyanion, while the ITE ending is used for the oxyanion with the same charge, but one less oxygen than that of the ATE ion. For instance, NO3- is called the nitrate ion, and NO2- is called the nitrite ion. Naming ionic compounds is relatively straightforward. It involves combining the names of the cation and the anion. The key to ensure that the charges of the ions balance each other out, resulting in a net charge of 0. For instance, if we combine the calcium cation Ca2+ with the oxygen anion O2-, we get calcium oxide, which is represented by the chemical formula CaO. Another example involves cobalt-2 and the hydride ion H-. When these ions are combined, the resulting compound is called cobalt-2 hydride, and its chemical formula is COH2. Remember that the charges of the ions need to cancel each other out to maintain electrical neutrality of the compound. Naming inorganic acid compounds builds upon previous knowledge. For anions consisting of a single element, we replace the ending with IDE. For example, the chlorine anion Cl- becomes chloride. To form an acid, we add hydrogen to the chemical formula, resulting in HCl. To update the name, we follow a specific pattern. We add the prefix hydro to the beginning, changing the ending IDE to IC, and append the word acid. Therefore, HCl is called hydrochloric acid. Different rules apply to anions with endings such as ATE, ITE, and so on. However, memorizing these rules is not crucial for becoming an excellent chemist. The last subunit in Unit 2 introduces us to organic compounds. Organic compounds are a class of chemicals that consist of carbon and hydrogen atoms. They form the vast majority of chemical substances, outnumbering all other types. Due to their abundance and complexity, a separate branch of science called organic chemistry is dedicated to studying and understanding these compounds. Organic chemistry focuses on the properties, reactions, and synthesis of organic compounds, reflecting their significance and widespread occurrence in nature and human-made materials, such as drugs. The simplest compounds containing only carbon and hydrogen are known as hydrocarbons. Among hydrocarbons, the most basic ones are called alkanes. In alkanes, each carbon atom is bonded to 4 other atoms, typically hydrogen. For example, methane consists of 1 carbon atom bonded to 4 hydrogen atoms. As the number of carbon atoms increases, the name of the alkane changes with the addition of specific prefixes to the ane ending. For instance, 2 carbon atoms form ethane, while 3 carbon atoms create propane. The ending ane remains constant, but the prefixes indicate the number of carbon atoms. When a single bond in alkane is converted to a double bond, the compounds are called alkenes. The naming of alkenes, the A in the ending ane is changed to an E, but the rest of the name remains the same. Similarly, if the double bond in the alkenes is further converted to a triple bond, the compounds are called alkynes. In the alkynes, the E ending in ene is changed to a Y, while the rest of the name remains unchanged. The alphabetical progression of A to E to Y, when going from 1 to 3 bonds, is a helpful mnemonic for remembering the changes in the endings of these hydrocarbon classes. Alkanes, alkenes, and alkynes are considered different functional groups within the classification system of organic compounds. These functional groups possess distinct properties from one another. Another distinct functional group is alcohol. Alcohols are formed when oxygen is added to one of the carbons in alkanes. Unlike alkanes, the naming of alcohols involves the changing in the ending where OL is added to note the presence of the alcohol functional group. Alcohol also exhibits different properties compared to alkanes. For example, let's consider methane, an alkane with a boiling point of negative 161.5 degrees Celsius or negative 258.7 degrees Fahrenheit. In contrast, methanol, an alcohol derived from methane by adding oxygen, has a significantly higher boiling point of 64.7 degrees Celsius or 148.5 degrees Fahrenheit. This demonstrates a difference of 226.2 degrees Celsius or 407.5 degrees Fahrenheit in boiling points simply by the introduction of oxygen. Thank you so much for spending your valuable time learning and bettering yourself. If you like the video and want to learn more, donate, or get tutoring, please check out my website, nocollegeneeded.org. You can use the code NCN for 20% off tutoring and any supplemental material.